Hello, I am Sude Nur Keleş and this is our Physics 211 project. In this project we tried to make a spectrophotometer with using affordable components. In this project we aim to observe the absorbance of different solutions. For this we prepared two different types of solutions. In the first type we prepared salt and water solutions with different concentrations, and in the second type we prepared colored solutions with using food colorings. In our experiment, we used CD as a diffraction grating since it created a wider spectrum. When tried with a prism, the created spectrum was very narrow, which would make the data collection very hard for the experiment. In order to choose our light source, we tried two different phones. The first one created a spectrum with blank spaces, so it was not suitable for our experiment. The second phone created a continuous spectrum, so it was chosen as the light source. To optimize the data collection, we decided to use a servo motor. To move it linearly, we printed gear system from a 3D printer. However, the gears didn't fit each other, so we could not use that printed system. Hence, in order to collect the data at the same points, we attached the ruler to our circuit. Also, the circuit was connected to an Arduino to make data collection more scientific. In our experiment, we use different components. The first component is our diffraction grating made out of CD, which creates our spectrum in this side of the shoebox. We have a light source in flashlight. We chose this because it has a continuous spectrum. We have our circuit, which detects our light, and this circuit is connected to a ruler to move the circuit in different positions. And lastly, we have an Arduino, which collects data. In the experiment, the solutions were put inside the shoebox, right in front of the slit that allows light. Then the ruler attached to the circuit was moved throughout the spectrum, and at each data point, voltage values were obtained from the computer. In our experiment, we used two different types of solutions. The first type was made using food colorings, and the second type was used making salt and water solution. In the first type of food coloring solutions, we use 0.5 ml of food coloring, 4 ml of water, and then we increase the food coloring amount to 1. We prepared 4 different salt water solutions, each with different concentration. The first one was 0.1 moles of salt, then this amount was increased to 0.2 moles, then 0.3 moles, and finally 0.5 moles. In order to calculate the absorbance of different solutions, the Beer-Lambert law was used. The Beer-Lambert law relates linearly the logarithm of intensities of incoming and outgoing light with the concentration of solution. To measure the wavelength of the spectrum, grating equation was to be used. Grating equation relates the diffraction order, wavelength, diffraction angle, and distance between each slit in the grating as shown. In the light detecting circuit, a transimpedance amplifier was used. In the transimpedance amplifier, the output voltage is given by resistance times current created by the photodiode. The current in the photodiode is linearly related with the illuminance, which is related with intensity. Hence, since voltage and current are linearly related, ratios of voltage values were used to calculate the absorbance. At the experiment with the food colorings, even though the absorbed wavelengths cannot be measured, we can see that as the concentration increased, the voltage values have decreased, leading to absorbance in the solution. As the concentration of the food colorings were increased, the voltage values have decreased more, leading to more absorption in the solutions. With the salt water solutions, as the concentration increased, the voltage values generally decreased. In order to calculate absorbance, the ratios of voltage values of water and solutions were taken, and their logarithms were taken as well. Unfortunately, in our setup we had many errors. The first one was due to putting the cuvette inside the shoebox. This caused light to refract and reflect, which changed the intensity of light observed. Another error caused by optical cuvettes was due to their shape. Since their shape were rectangular, the corners acted like a prism, creating their own spectrum, which affected our intensity measurements. Also, due to the positioning of our diffraction grating, the absorbed wavelengths could not be calculated because the diffraction order of the spectrum was not known.